Let us now see the continuous analog of conditional distributions. Okay, and now let's look at the same probability that we did over here, which is probability that x equals some s conditioned on y equals 0. Okay, and of course this value will be equal to 0 in continuous random variables, and the reason is that for continuous random variables, the probability that x is exactly equal to any value is actually 0. So we should actually be talking about the conditional distribution. Okay, so I will call it the conditional PDF. Okay, and this will be denoted by px conditioned on y being equal to 0. Okay, and 0 is just an example. You can replace it with any t that you want. And the definition of this will be equal to, will be the exact analog of what we did for the discrete case, which is we look at pxy of s comma 0. So remember, we are interested in the density value at x equals s. Okay, so this is why this is on the numerator, and the denominator, remember, if you remember what we did over here in the simple case, we summed over all the possible values of x while setting y equals 0, right? So we summed over this whole column, and now the analog of the sum will simply be the integral. Okay, so this will just be integral over all choices of x. Let me use a new variable z. Okay, so we have px y of z comma 0 dz. Okay, so this is exactly the analog. So this is of the discrete case. So on the numerator you have the probability at s at x equals s conditioned on y equals 0, and here you just have total probability while conditioning on y equals 0. Okay, so this is what we call the conditional PDF, conditional distribution of x given y equals 0. All right, so this defines the notion of conditional distribution and marginal distributions for different variables, for jointly distributed random variables. So let's now go back to the examples that we had. Okay, so these are the 3 examples that we had. Let me copy paste this example, and let's work out a few of these a few of the explicit values for some of these things. Okay, so let's see if I can copy paste this. Okay, so I have so these are my examples. All right, so let's look at example 1 for now. Okay, so example 1 is the easiest of the lot. So here what you should observe is that if you sample a random point from the square, right, so the x coordinate and the y coordinate are independent of one another, because if you sample any x, so any point out here, the x coordinate has a certain distribution, But conditioning on, let's say, the x coordinate having certain value, the distribution of y remains the same, because for any x, so in example 1, fixing any value of x, the distribution of y is still the uniform distribution, the uniform distribution over minus 1 1. Okay, so in this case, what we have is that the conditional distribution, so that is py conditioned on x equals s for any s, is exactly the same as uniform distribution over minus 1 1. Okay, and interestingly, so in this case, this is also the marginal distribution for y. Okay. Also the marginal distribution for y. Remember, the marginal distribution is simply, you look at the distribution of y not caring about what value of x is, because the distribution of y is the same for any value of x. You have that the marginal distribution is exactly the same as uniform minus 1 1. Okay, so this is equal to uniform minus 1 1. Okay, and so variables that satisfy this property, so if you have joint variables x and y such that conditioning on some value of x, the distribution of y does not change, such variables are called independent random variables. So let me just define this. So if we have jointly distributed random variables, or in other words, if we have random variables x and y defined over the same sample space omega, then x and y are said to be independent if the conditional distribution of x conditioned on y equals s for any s, or y equals, let's say, t, is the same as the marginal distribution of x. Okay, and the same is true if we replace x with y, okay, by swapping the roles of. Okay, so if you have this property, then the random variables x and y are said to be independent. Okay, so this example of random point in a square is one simple example of in which you get independent random variables. So in general, you get independent random variables if let's say you perform an experiment twice, and x is a random variable that you get as the outcome of the first experiment, and y is the outcome of the second experiment. And suppose these experiments have nothing to do with one another. in the sense that you repeated the entire setup, then the random variables tend to be independent. Okay, so let's look at the second example. So here the random variables don't turn out to be independent. Okay, so in example 2, so in this case you have point that is sampled from a tilted square. Okay, so now the thing that you should notice right away is that let's say I condition on x equals 0. Okay, so that means I am on this line. So in this case, what is the conditional distribution of y, right? So every point in the square is chosen with equal probability. Therefore, every point on this line is now chosen with equal probability, right? Because I am conditioning now on the fact that you are on this line. Okay, so the conditional distribution of y will simply be the uniform distribution over -1, 1, because the value of y can lie anywhere between -1 and 1, and each point on this line is equally likely. So any point on this line is equally likely. Therefore, you get this distribution to be uniform -1, 1, conditioned on x equals 0. So now, what if I condition on of y conditioned on x equals, let's say, a half? Okay, so x equals half is somewhere over here. Okay, and now conditioning on x equals half means that your point, the point that you're picking, is somewhere on this line. Okay, and what does being, and we know that every point on this line is equally likely. Therefore, this conditional distribution would basically be the uniform distribution over minus half half. Okay, and note that these two are not equal, right? So these are not equal. Okay, therefore x and y are not independent. Okay, and in this case you can also ask, what is the marginal distribution of x?